we're going to combine a couple of different concepts together in something called gas stoichiometry. Now, we've learned a lot about gases and gas laws. We've also learned about stoichiometry previously, so we're going to put them together into something that's actually really not that different than what we've done before. It's just a matter of keeping track of what you've got and how you can apply it. So as you can imagine, lots of reactions do occur in the gaseous phase. Lots of reactions, of course, that we think of a lot of times happen maybe as liquids or solids, but many definitely happen in gaseous phases. And anytime you deal with these, we can kind of assume that the solids and liquids don't really have anything to do on like pressures and volumes. You know, for example, let's say you have a container here and you've got some liquid that's in here, and then, you know, it reacts and there's some gases that are involved. The volume of this container is going to be occupied by some of this liquid that's right there. Right? So some of the gas pressure that you can measure about this may actually be slightly affected by this liquid that's at the bottom. But again, we're just going to assume that that's not going to play a role. So whatever is the container size and the gases in it, we're going to assume that's the same gas volume, and not to have to consider that little bit of liquid or even whatever solid that might be at the bottom too. Anyway, with gas stoichiometry, it relies on a balanced chemical equation and mole quantities, just like any other kind of stoichiometry that we do. So it all comes down to mole ratios and being able to figure out how those are applied. When it comes to doing these problems, you'll basically see there's a couple of similarities, and more than anything, again, find that reaction equation, whatever it might be. Sometimes they give it to you, sometimes you have to figure it out yourself. Mole amounts are also your friend here. Anytime you're given some pressures and volumes and such, you can do some work to help you figure out how many mole or how much moles are in that sample. And then from there, you could do your stoichiometry and whatnot. There's a possibility that limiting reagent can be involved too, but you know, anything that revolves around stoichiometry all revolves around mole amount. So get the pressures and volumes and temperatures and do some equivalent mole amount. And of course, at some point, you might have to convert them back into gas quantities, you know, so still have to go back to doing the gas and pressures, or figure out how much volume is there. And so that's something that you can rely on. Once again, it's all about some mole amounts, but if you need to, switch them back and forth between gas quantities. Finally here, use molar volumes when possible. All right, so molar volumes, if you remember, that's the idea that at STP, right, so at standard temperature and pressure, where temperature is 0 degrees Celsius or 273 Kelvin, and at standard pressure, which is at 1 atmosphere of pressure, or whatever equivalent unit in millimeters of mercury or torr or kPa. So at this set of conditions, every single gas is assumed to occupy 22.4 liters for every 1 mole of whatever gas you may have. So that's a nice number to, again, have handy there. So at STP, any gas will have 22.4 liters per every 1 mole of that gas. So let's go and take a look at one example here. This one starts off by talking about calcium carbonate, which is often the main component of limestone. It can be heated to produce carbon dioxide and calcium oxide, also known as quicklime. If 152 grams of limestone is decomposed, what volume of carbon dioxide at STP will be produced? Okay, so let's go and see what we have here. This balanced equation is provided. Notice that you do have some solids here, and you also have the important part, which the question is asking you about, is going to end up being CO2 as a gas. So ultimately, your goal, the problem that what it's asking you for, is what volume of carbon dioxide will be produced. And also a nice thing to know is that they say at STP. So just like we said a minute ago, that molar volume thing can be applied. All right, if you don't have conditions at STP, you can't apply that molar volume of 22.4 liters per mole. Either way, let's go ahead and put this one together. We are given 152 grams of limestone, so we're given 152 grams of this substance right there. And then we're asked to figure out information about this substance over here. So as you can imagine, if we have two substances in one equation, we're going to have to use some stoichiometry to help us figure that out. Thankfully, this thing is balanced already. I don't know if you actually looked at it yet, but it's actually already balanced, so it's all coefficients of 1. Either way, we still have to show the work like we usually do anyway. So just to kind of give you a heads up, this molar mass of calcium carbonate ends up being 100.09 grams per mole, something that you can definitely look up on your own. I just did it for you there. And then we go start this off. We're given the CaCO3, given this substance here, and then we're going to find some information about our substances. Well, we got to get from calcium carbonate to carbon dioxide. Can't use a gram amount to make that happen. We're going to use instead mole amounts. And so we plug in the molar mass, so the appropriate units in the right spot for every 1 mole of this substance. Right? And then we go ahead and apply the mole ratio, because we have mole amounts of calcium carbonate. we can then get the mole amount of carbon dioxide, which is our goal substance. So for every 1 mole of calcium carbonate, we're going to produce 1 mole of CO2. So this is going to get me a mole amount of CO2. So if I pause here again, this would be on the right path. But ultimately, it's asking me for the volume of carbon dioxide. All right, so this is not a volume. A mole amount is not a volume. So one of the nice things, again, is that, as we stated before, is that if we know that this substance or this conditions are held at STP, at that temperature and specific pressure, the relationship is that for every 1 mole of a gas, you're going to have 22.4 liters of that substance. It just happens to be that much. And then you do some math here, and you can rearrange and calculate and whatnot, and then you end up getting 34.0 liters of CO2 gas that is going to be produced by decomposing 152 grams of limestone. So this again is basically stoichiometry, right? Everything up to that very last step was stoichiometry. The only thing you had to include now was the fact that that molar volume, that idea that 22.4 liters per mole is a thing at STP, then you just stick that in, and just like usual, you cancel off the units you need to, and then you end up with the unit that you want, which is volume, a liter amount of CO2. Let's try the next example. For this one, you have 0.458 atm of nitrogen gas, and it's added to a 1.50 liter flask with an excess of oxygen gas at a temperature of 244 degrees Celsius. Nitrogen dioxide gas is the only product. Okay, so this is your prompt here. You have a couple of sort of leading problems here to help you out with the final answer. Write a balanced equation for the reaction. I'm going to do it above so I have a little bit more space underneath it. First of all, nitrogen gas, remember these are Brinkelhoff elements, right? Nitrogen gas, that's going to be N. And that's going to have the gas label, and then it's going to be reacted with some oxygen gas. It's going to be O2. And then you're going to produce some nitrogen dioxide gas because it tells you that's the only product. And of course, nitrogen dioxide, that's going to have a formula of NO2, and that's also a gas. So all these are gases. It's kind of nice to know that. Also, if you see that the equation is there, you don't really have it balanced just yet. So let's make that happen. To do so, I think you would probably do a little bit of this and a little bit of that. All right, so now we have a balanced chemical equation. Now the rest of the problem can be accomplished. So this goes back to some information and some abilities that you have from an old unit. Okay, let's keep this party going. We got that taken care of. How many moles of oxygen gas are needed to fully react with the nitrogen gas? So remember that this language of having an excess of oxygen gas, that sometimes might, make you think about excess reagent, limiting reagent. But remember, you don't have to have that information because you're not really asked about figuring out how much product there is or which one's your limiting reagent. Well, partly because you already know what the limiting reagent is going to be. It's going to be this nitrogen gas because it tells you that the oxygen gas will be in excess already. It doesn't matter how much is there, just know that there's going to be an abundance of it. But now the question is, how much of that abundance do we actually need to fully react to that nitrogen gas is provided? All right, so how many moles of oxygen gas are needed? Well, again, if I got to get mole amounts of oxygen gas, I don't really have any information about that gas itself, except for that you have a mole ratio of 1 to 2 between nitrogen and oxygen. So again, I don't have anything specific to oxygen, but I can get information about oxygen if I use information from some other substance, in this case, nitrogen. So they're asking me for a mole amount of oxygen gas. I would like to have a mole amount of nitrogen gas because if I'd had the mole amount of nitrogen gas, I can very easily apply that mole ratio. But unfortunately, again, I don't have mole amount of nitrogen gas immediately available. But what information about the nitrogen gas do I have? I do have that it has a pressure in this container and it's got this temperature. So I have a pressure of nitrogen, I have a volume of nitrogen, I have a temperature of nitrogen. Is there a way that I can apply those to be able to figure out a mole amount? Absolutely. Remember this formula, PV equals nRT, where this is the ideal gas law. So for nitrogen, right, let's go and do some work on nitrogen here. For nitrogen, I can plug in some numbers and then basically solve for my mole amount. So pressure is 0.458 atm. The volume that it's contained in is 1.50. The mole amount, the N, I'm solving for. The R is that gas constant, 0.08206 liters atmospheres per mole K, all of that together, and then times your temperature. Well, again, I can't plug in 244 degrees Celsius because, well, it's got to be in Kelvin. So that work right here, 244 plus 273.15, that results in 517, that's 517 Kelvin, right? take that, plug it in here, 517. Okay. All right, so we have this setup right here. This will eventually solve for the mole amount of N2, which I can then rearrange to solve for. That's 0.0162 moles of nitrogen gas that is going to be in that container. Right, so that container, again, I don't have the mole amount provided to me, but I can use the rest of the data points to help me figure that out. All right. So the problem is, though, again, is not asking for mole amount of N2, it's asking for the moles of oxygen gas. So this is a step to help me get a mole amount of N2. Well, at this point, right, again, you should be able to handle this one because you have a mole amount that's provided to you. You have a mole amount which you're solving for, and all you need is a balanced chemical equation, which is something we could do from months ago. So let's make that work. It's going to be 0.0162 moles of N2. I'm going to go ahead and use my mole ratio for every 1 mole of N2. I'm going to scooch back up here so you can see it. For 1 mole of N2, you're going to have 2 moles of O2 produced as a result of the reaction, right? Or excuse me, in this case, 2 moles of O2 that will also be needed to react, excuse me. So we're going to have a value of 0.0324 moles of O2 that's also needed to react with that initial amount of N2, right? The one that's 0.458 ATM, 1.50 liters to 244 degrees Celsius. So all the information right there kind of gives us one nice clean number here for the mole amount of O2. That takes care of number dos. How many grams of nitrogen dioxide gas can be produced? All right, so how much is going to be produced here? All right, so we know that, again, our limiting reagent, as I said before, is going to be the amount of nitrogen gas that was initially given to us, right? So that was provided at the beginning of the problem. Now they're asking for grams of nitrogen dioxide gas. They're asking for amount of product. Now, you might be, again, thinking about limiting reagent, but because you have 2 reactants and such, but you're kind of already told that the limiting reagent is that nitrogen still. We just know that there's going to be plenty of oxygen around, so the only thing that's going to be limiting our reaction overall is going to be the nitrogen. Well, thankfully, we also have the mole amount of nitrogen we're provided with in the beginning, so all we have to do, again, is just go ahead and take the mole amount of N2 and figure out the mole amount of NO2 and then get that into grams. Let's see how this works. So that 0.0162 moles of N2 that's provided at the very beginning. For every 1 mole of N2 gas, it's going to produce 2 moles of NO2 gas. Right? And then at this point, right, because we're not asked for the mole amount of NO2 that can be produced, we're asking for the gram amount. We have to take that molar mass and figure out with NO2 and then figure out how many grams that produces. So that's over. So for every 1 mole of NO2, that's 46.01 grams of NO2. Again, not provided to you anywhere in the problem. You have to add that up on the periodic table. Do a little bit of math here, and then you end up getting a value of 0.745 grams of NO2. And that's your final answer there. All right, so I'm hoping that when you look at this and you work through this problem with me, you're finding that this is really not that different than what we've already done in the past. When it comes to the stoichiometry part, the only additional part that we have to address is the fact that we do have gases to maybe consider. Generally speaking, we're not really going to change a whole lot other than that, right? So if you're given some gas quantities like moles and pressures and temperatures and such, you can rearrange and solve for the part that you need to. And as you can tell here, basically all we've done that's really different is really just in step 2, right? Step 2, that's the only one where something new is introduced compared to the old stoichiometry we used to do. Everything else follows the same pattern. Okie dokie, that'll do it.